Okay, we're going to be talking about Taylor polynomials here, and we've talked about Taylor series before. All right, so let's take a look at the definition again, and this is very similar. Taylor polynomial of order n is very similar to the definition of the Taylor series that we talked about. But it says let f be a function with derivatives of order k for k equal 1, 2, all the way to some number n in some interval containing a as an interior point. Then for any integer n from 0 through n, the Taylor polynomial of order n generated by f at x equals a is the polynomial, we're going to call it p sub n of x, which is f of a plus f prime of a times x minus a, plus f double prime of a over 2 factorial times x minus a squared, and so forth and so on, so that you end up with the nth order derivative of f at a over n factorial times x minus a to the nth. So there is a pattern to this. All right, there is a pattern when you are generating these Taylor polynomials. So let's go ahead and take a look at a very simple example here, number 5. All right, and I say this is simple because it is a linear function that we're going to be taking a look at. All right, and let me actually write out the instructions here. All right, let's see what it is. Let's say find the Taylor polynomial generated by f at x equal a. So there are the instructions. All right, so let's take a look at number 5 now. All right, so this is going to be f of x equals 3x minus 6 at a equal negative 3. All right, so we've got to find a couple of derivatives here. All right, so we have f of x, so let's find f prime of x. F prime of x is 3. F double prime of x is going to be 0, and we really can stop there. All right, so let's take a look and see what we get. F of 3 is going to be 3 times 3, which is 9 minus 6, which is 3. F prime of 3 is just going to be a constant, which is 3. And f double prime of 3 is just 0. So now we have enough information to write out our Taylor polynomial p sub n of x. So what does that look like? Well, that's going to be, let's see here. Okay, I'm sorry, it was negative 3. That makes a huge difference here. Let's go back and adjust that. Sorry about that. F of negative 3 is 3 times negative 3, which is negative 9 minus 6. This is negative 15. F prime of negative 3 is going to be, again, 3, and that's still going to be 0. So that makes a little bit of a difference here. All right, so we start off with f of negative 3, which is negative 15, plus we're going to find f prime of negative 3, which is 3, times x minus negative 3. All right, so x minus negative 3 really becomes x plus 3. So let's go ahead and write it as x plus 3. And there's no need to write f double prime because it's 0. All right, but of course you would have to multiply this by 1 over 2 factorial if you were going to continue, if there was something other than 0 there. But what I want you to do is I want you to see the connection. Look at what happens. If you evaluate, or if you expand this 3 times the x plus 3 and you subtract the 15, you're going to get f of x equal 3x minus 6. They are equivalent. So that's really interesting, but this is very noticeable when you're dealing with polynomial functions. Not very noticeable if you're dealing with maybe a rational, but I want you to see how it's generated by all of this. Okay? I want you to see how that occurs. All right, let's take a look at one last example here. All right, here's the last example, number 6, and we're going to say f of x equals x squared plus 6x plus 5, and we want to find this around the number a equal negative 2.
I didn't get that.
And you'll have to excuse that little computer voice there. All right, so f of x equal x squared plus 6x plus 5, a equal negative 2, and these are very low budget videos, so I do apologize. Let's find f prime of x first. So f prime of x is going to be 2x plus 6. F double prime of x equals 2. And f, the third order, f triple prime of x is just going to be 0. All right, so let's find out what f of negative 2 is. F of negative 2 is negative 2 squared, which is 4. 6 times negative 2 is negative 12 plus 5. 4 minus 12, negative 8 plus 5, this is negative 3. And then we're going to find f prime of negative 2. And we're going to have 2 times negative 2, which is negative 4 plus 6. Let's see. One little second here. I'm going to make sure I didn't mess anything up this time. All right, so I have 2x plus 6. I plug in my negative 2 for sure. 2 times negative 2 is a negative 4 plus 6. That's a 2. All right, so we get that right there. Okay, that looks good. All right. And then we're going to check f double prime of negative 2. And what does that look like? Well, that's going to be just a 2, but then we have to multiply it by 1 over 2 factorial, which is going to give us a 1. All right, and now we check the third order, but the third order derivative at negative 2 is just 0. You again could multiply it by 1 over 3 factorial, but there's no need. It's just 0. All right, and I think now we're ready to write out our Taylor polynomial here. All right, we're ready to write out our Taylor polynomial p sub n of x. All right, let's see what we get. We get f of negative 2, which is a negative 3, plus f prime of negative 2, right? F prime of negative 2 is going to be this 2 times, let's see, x minus negative 2, which is just going to be x plus 2, correct? Write it as x plus 2. Plus, in this case, it's going to be a 1, so we don't need to write the 1, but we do write x minus a negative 2 squared, which is going to be x plus 2 quantity squared. And it looks like that. So, this one, I will kind of do the expansion just because I want you to see this is the answer right here. This is the Taylor polynomial. All right, and that was the Taylor polynomial there. But let's go ahead and try to work this one out. Just want to do the quick expansion, and I'll do it in a different color. Negative 3 plus, and then 2x plus 2. 2 times x plus 2 is 2x plus 4, plus x squared plus, this is 4x plus 4. All right, when we combine the like terms, we're going to get an x squared plus 6x. Negative 3 plus 4 is positive 1, plus 4 is 5. And I want you to see the connection again. There you go. There you have it. Really nothing to it. There it is. There's your Taylor polynomial right there in red. But I want you to see how it expands to give you the original function. And it was all working with derivatives. So it's kind of neat how this actually works out. But this is a little bit on Taylor polynomials. So as always, I hope this video was helpful. And remember, like and subscribe.